Okay, I think we have a pretty good showing considering how many things are going on. So there's obviously a lot of interest. For everybody who's here, great to have you here. I'd like to introduce Dr. Kennedy Ned Rubert-Nason. He's a chemical ecologist with a PhD in molecular and environmental toxicology from Wisconsin-Madison. And he has his undergraduate degree in environmental chemistry from the University of Virginia. He co-funded the inclusion section of the Ecological Society of America, served as a Hughes Teaching Fellow, is a consistently published author, and loves doing all things outdoors, particularly skiing and whitewater kayaking. And his scholarship explores how climate change impacts forests and promotes sustainable forestry for climate change mitigation and adaptation. Ned is giving his presentation today as part of membership in our institute, which we're very excited to have him join because it's always we can't say that we are experts by any means in forestry, forests related to climate change, and also to help us establish a stronger relationship between us and the University of Maine, Fort Kent, which has tons of opportunities and some very impressive faculty like Ned. So please take it over, Ned.
Well, thank you very much, and I'm grateful for the opportunity to speak with all of you affiliates of the Climate Change Institute and others who may be joining to learn about the amazing scholarship that we're doing up here in Fort Kent that is largely focused around sustainable forestry in a changing climate. And before I get too far along, I like to build a little bit more off of what Paul said in terms of bringing in my background in philosophy, as this guides a lot of the work that I now do. And as you'll learn pretty quickly, has a different perspective than is common in a lot of the scholarship that happens on larger university campuses. So as Paul mentioned, I have a Bachelor of Science in Environmental Chemistry from University of Virginia. PhD is in Environmental Toxicology from University of Wisconsin. And then I followed that up working as a postdoc and later a staff scientist in Professor Richard Lindroth's lab. And his interest was chemical ecology, focused on using populace, that is aspen and cottonwood, as a model organism to understand the effects of climate change and also to really probe the ecology of poplar insect interactions. Some of my favorite activities are skiing and whitewater kayaking, and that actually plays into guiding a lot of the work that I now do, as well as a number of experiences doing activism for the benefit of Indigenous communities in the North Woods of Wisconsin and raising some concerns about mining and the impacts on the plants, animals, and waterways of that region. I've also published in a number of areas, including method development using infrared spectroscopy to map different plant traits in changing environments. I'll mention a little bit later on, I've published in social sciences as well, particularly as it relates to building partnerships for doing science. So in summary, my scholarship explores how climate change impacts forests and promotes sustainable forestry for climate change mitigation and adaptation. So when I do science, I look at it not only from a reductionist perspective, but also as a holistic perspective that includes humans and how they participate in doing that science and what the outcomes are on humans and the other organisms in the physical environment. So the rationale for my research broadly is that healthy forests are necessary to mitigate climate change. That's true for a number of reasons. They can take up and store carbon dioxide. They're a source of renewable energy that does not require us to depend on fossil fuels. They can clean the air of a variety of other pollutants that are bad for human health. And I'll also give a pitch for what our indigenous people have figured out thousands of years ago, that humans like to live in a green environment. If you read a number of publications in public health and social sciences, there's quite a bit of evidence saying that people are healthier and happier when there's green spaces around them. The map here on the right shows, at least if we look at the green areas, shows the densest forested areas in North America. The bottom line being that much of the eastern part of the US, as well as most of Canada, is covered in trees. And climate change also has a variety of impacts on trees. In summary, when precipitation patterns change and things get warmer, the trees that are adapted to growing in various areas become less healthy and potentially die. There's also a variety of indirect impacts, such as changing the distribution of pathogenic insects and fungi. That can range from creating environments that are more hospitable to colonization by non-native invasive pests and pathogens, and also transforming native insects, such as some of the bark beetles, into organisms that are tremendously damaging to our trees. Climate change also has a lot of other indirect impacts, such as the tendency to bring about more frequent, more intense forest fires, and even the not very visibly apparent oxidative losses of soil carbon, which tend to increase as temperatures increase. And that can change many of our forest soils from being reservoirs or sinks of carbon into potential sources of carbon to the atmosphere. And of course, if we start losing large areas of forests, as we're seeing in parts of the American West right now, there's tremendous impacts on human livelihood and well-being, ranging from health impacts to property loss. Before I delve further into some of the scholarship I'm doing here and now, I'd like to give brief attention to broader impacts, and specifically that I focus a lot of my work on shifting paradigms to ultimately, hopefully, and optimistically lead to creation of more sustainable forests that promote human livelihood and well-being in the context of a changing environment. Through that, we can also still do a lot of that fundamental science that we value so highly in our culture, deepening understanding of how climate impacts forest ecosystems, and developing innovative practices for redesigning our forest ecosystems so that those are economically valuable and provide the services that humans desire for years to come. Through this work, I've also increasingly engaged the Indigenous communities and continue to do so in my present work. So with that, I'm going to jump into part one of the two prongs of my scholarship. Prong one being more descriptive and focused on deepening knowledge of how climate change impacts forests, with a specific focus here in Maine. One piece of this is microclimate reconnaissance. That's a fancy term for explaining that I'm coordinating some efforts for measuring weather and climate conditions at different sites in northern Maine. One of these, the site at Debooley, has been co-organized as part of the NSF Inspires Northern Forest Data Collection Initiative with collaborators at UNH and at Maine, and then also courtesy of some funding that Dr. Nicole Rogers and I formerly acquired a few years ago. We've installed several of these small climate monitoring stations shown at right. One is a demonstration site on the UMFK campus. One of them is near Eagle Lake, and the third one is over near Cross Lake. And the station at Cross Lake also serves the purpose of helping this partner organization, Friends of Cross Lake, get a clearer picture of changing precipitation and temperature dynamics that are impacting the water quality in the Fish River chain of lakes. So much of that is their project, but this initiative here is providing data that directly supports their water quality initiatives. The first big project I had up here in northern Maine, which is continuing as Dr. Peter Nelson and I move from presentation towards publication of our data. And it's specifically focused on rapidly detecting changes in tree health, specifically populus and spruces, in response to environmental conditions. Fundamentally, the way this worked is we picked about 300 trees in two taxa, that is populus and spruce. We measured a variety of observations of physical, physiological, and phytochemical traits on the ground. And then we also concomitantly imaged those trees with infrared and vis data using drones, really aimed at answering the question, to what extent can we use hyperspectral data to predict these traits that can be measured on the ground, but do so at a much faster, more affordable way. Again, we had Dr. Peter Nelson and his colleagues were flying a drone such as the Phantom Matrice, shown here at the left, over 6 different study sites in the North Maine woods, which look much like we see on the right. And then I was involved with leading a group of undergraduate students on the ground, and we collected a bunch of different data, including classic forestry metrics of tree health, things like vigor class, crown density, specific leaf area, all of which are known to be tied to tree health. We looked at maximum photosynthesis rate and stomatal conductance under light saturating conditions, chlorophyll fluorescence, which is also widely known to change in response to plant stress, along with a variety of phytochemical endpoints such as nitrogen, carbohydrates, and condensed tannins in the foliage. We ultimately synthesized those data together, created n-dimensional correlations or regression models that relate the hyperspectral data that we mapped on these different trees with individual traits that we measured on the ground, and showed that in most cases we were able to successfully model those data. I'm going to start off with a series of graphs and charts showing the extent to which we could effectively model these phytochemical traits, starting off with answering a key question of to what extent can we distinguish among closely related tree species using hyperspectral data. The answer is yes, although I'd like to see us be a bit more accurate than we are. And the reason why species identification here is important is because the ability to accurately quantify different plant traits is highly correlated with species. So we have to be able to identify species first, then we can identify and map the traits. So yes, we can identify closely related species. We can predict common forestry metrics such as vigor class, which I like to describe in a very succinct way to my students. Does the tree look like it's really healthy and happy? And is it all green and have full branches? Or is it like ugly and half dead? Um, the next several graphs that I show, we're going to have the predicted or validation on the y-axis and the input or calibration values on the x-axis. These are called confusion matrices. They're a little bit harder to interpret. So I'm just going to focus on accuracy. But as we move into the continuous trait variables such as crown density and specific leaf area, we can think of these maps here as being like a correlation graph with the individual color data points being related to individual measurement points. And if you have more frequent occurrence of those, you get a different color density on the heat map. Again, we're using a pseudo R² for these n-dimensional correlations. All of the R² values I'm going to be showing are statistically significant. Of course, higher, closer to 1 is better. But these without, I'm going to step back here a moment, say without a lot of refinement of our predictive models, we can show that crown density and specific leaf area can be predicted from hyperspectral data, as can the ecophysiological endpoints. This one I was actually very happy to see because when we undertook this project, considering how much uncertainty there is with collecting these field-based measurements of things like maximum photosynthesis rate and stomatal conductance, or how efficiently water is transmitted through plant stomata. These measurements are very cumbersome, very error-prone to collect. So I was actually quite delighted to see that we were able to make meaningful predictions based on our field data. And we also were able to get useful predictions from the chlorophyll fluorescence. The one downside we figured out here is that the chlorophyll fluorescence was not all that great of a predictor of plant stress, considering that the only time that we saw meaningful decreases in fluorescence ratios indicating stressed plants, the trees looked like they were basically dead and were dead within the next year. So this was not as good an indicator of early warnings of plant stress as perhaps some of the other traits. We also looked at phytochemistry, and the rationale here being that changes in plant health, especially plants that are either stressed for resources or stressed by perhaps too much heat or too much cold, tend to show changes in accumulation of carbohydrates in the leaves outside of what would be considered an optimal range. And again, we're not even getting too much into the weeds here, but suffice to say, we were able to successfully map and predict changes in carbohydrate levels in these different tracts of land that we measured. Foliar nitrogen can also be very nicely mapped with the hyperspectral data, as can condensed tannins. So in conclusion, we can successfully use these drone-acquired hyperspectral data to map plant health traits that are indicative of changes in plant health. In this particular project, we did nothing to prove whether or not climate was causing the stress. This was simply a way of showing that we can use these hyperspectral methods and drones to more quickly identify changes in tree health and the traits indicating that. Some of these measurements, particularly things like vigor class and foliar nitrogen, were predicted very well. Some of the physiological traits were less well predicted, but again, given all of the potential sources of error in data collection, that's not surprising. Moving forward, one of the things that Dr. Peter Nelson and I would like to do, and this is more in Peter's realm, is the GIS and the geospatial person, is going to be building a holistic model that allows us to combine all of the different traits that we looked at into one type of model that basically gives us a numerical output indicating the probability that a plant is stressed. Potentially, we could also launch future projects off of this one to see if we can identify signatures of particular types of stress, such as, is the tree heat stressed? Is it stressed by damaging insects or fungal damage or something else like that? All with the main goal of being able to more rapidly identify changes in tree health at a landscape change so that we can target faster and more effective and more targeted interventions, whether those are potentially early harvest before trees are dead. As many of us in forestry know, an unhealthy but living tree with good wood in it is worth a whole lot more than a dead tree, and potentially even take actions that keep those trees from dying. With that said, I'm going to move on to some other projects that are up and coming. One of those is starting this coming summer. I'm going to be working with Aaron Weiskittel, Peter Nelson, as well as some colleagues at Purdue University, John Couture, and Melba Crawford, to continue work with this trait mapping as part of the Perseus project, which again does a lot of things. It's all focused on promoting economic resilience and sustainability of Eastern US forests. Building in a climate change context is really vital to the long-term management of many trees that we have here in Maine, such as our spruces, as well as some of our hardwoods like maples. And specifically, what we're going to be doing this coming summer is modifying the work that I just described to use a broader band infrared sensor and some more up-to-date technology that's going to give us a higher resolution spectral data with more accurate geolocation. We're going to pick at least 3 different study sites across a transect from northern Maine to down east. In each of those sites, measure approximately 3 regions within those sites. And instead of looking at only populus and picea or spruce, we're going to look at hopefully around 27 of the most common tree species in Maine and try to create similar validations for predicting around 10 different traits in each of those different species. So with a brief pause, I'm going to move into the second dimension of my work, which is focused on more on applications and how do we actually go about building healthy forests rather than simply showing where there are potential problem areas. Currently, the big thrust I have in that area is using biochar Biochar has gotten trendy in recent years, and there's some good reasons for it. Um, One, it can be made from trees, so it is a renewable resource. It contains carbon. And the way we typically create biochar is by partially combusting wood. So you set wood on fire and then you reduce the oxygen such that the wood does not completely combust. Some of that carbon will be lost, but a lot of the carbon is also retained and it's converted to what is essentially charcoal. And unlike wood that you might leave on the ground to rot, when you put charcoal on the ground, it actually doesn't decompose very quickly. It tends to be fairly chemically stable in this reduced state, such as I have shown here on the right. And that has the potential for increasing the longevity of that carbon once it enters soil. Whereas typically things like wood and leaf litter, if you leave it sitting on the ground, it does decompose. Some of that carbon ends up in the soil as microbial biomass, and a lot of it also ends up gradually oxidizing to carbon dioxide and going back into the air. So again, biochar is potentially a useful product for increasing long-term storage of carbon. It also can be made from trees, particularly parts of trees that are not otherwise usable for forest products. So things like salvage logs, logs that are rejected because you cut down a tree and it's hollow, the slash that is not as usable for making other products. And it can also improve nutrient and water retention in soil. The water retention in particular is another important aspect of climate change mitigation. We focus on Maine. One of the forecasts that's noted in the Maine climate report is that we're likely not only to get warmer, but have increased variations in precipitation. And in many areas, the consensus is things will perhaps get wetter, but the devil is really in the details and these variations in precipitation. If we look at parts of northern Maine and also the mountains, we have very thin soils that are either rocky or gravelly or sandy. And so when you start having more variable precipitation, you run into water stress in trees and other plants because of inadequate water retention during those dry intervals. So the big project that is just getting started right now, courtesy of funds from the Maine Economic Improvement Fund that were awarded beginning of last summer, is Dr. Ling Lee from UMaine, myself, Stephanie Landry, and Leben Lewis have set up this large 256 tree container garden to evaluate the effects of biochar soil amendments on water retention, soil carbon retention, and drought resilience in 4 different common tree species. So again, the first question answered by this experiment is going to be, can biochar promote tree growth and drought resilience and soil carbon storage? And then more broadly, can we use these types of practices to promote healthy forests in a global change scenario? I'm going to be starting a project this coming summer looking at effects of biochar on soil microbiomes and how that relates to applications as well. I'm going to focus here primarily on the setup of this large container garden study, which is a 3-year study. We did a little bit of data collection last fall, but again, 2024 was primarily focused on setup of this experiment. And this coming summer and summer 2026 are going to be the big data collection years. I mentioned before, we've got 4 different tree species, sugar maples, poplars. My preference would have been to use trembling aspen, which is a common tree in the North Woods. It's also one that is very commonly studied and a representative broadleaf species. We ended up with balsam poplar because of a problem accessing trees, but it's also a really cool organism to work with. Norway and white spruce, because those are popular silvicultural species here in Maine. Particularly, J.D. Irving has taken an interest in planting Norway spruce in their new forestry work. And over the next 2.5 years, we're going to be measuring a variety of endpoints, including vigor class, and by year 3, crown transparency. We're going to measure tree growth rates. I've got some additional funding through some parallel projects. We're going to look at soil microbiomes and how those adjust to the biochar use. We're going to do some phytochemistry work, looking at carbohydrates and potentially carbon-nitrogen ratios in the leaves, and whether the biochar applications or the water manipulations in this study impact those endpoints. And at the end of the experiment, we're going to do a big destructive harvest where we can measure biomass ratios to determine root to shoot allocation, which is a way of understanding how the tree, how resilient or not resilient those trees are to potential limitations and things such as water. In parallel, I'm looking at soil carbon retention. I have a cool gadget called a soil respirometer that's going to allow us to measure in real time respiration rates or losses of CO2 from the soil to show the extent to which the biochar that we add actually stays in the soil. And then that will be followed up with sending soil samples in years 2 and 3 from each of these pots to the Maine Soils Lab so we can do a full mass balance on that. Now, in the excuse me here, in the last couple of slides, I want to take all this work and really frame it in a broader context. I was told that since this is a research presentation, I'm supposed to focus on scholarship, which is awesome. I love doing that. The reality is that scholarship is about 1/3 of what I do up here in Fort Kent. We are primarily a teaching institution. And the way that I'm able to remain a productive scholar and keep up with teaching is to take a much more integrative approach to doing both. So as many students who know me would say, there's not a big distinction between my teaching and my scholarship. I'll often bring in examples of what's being done in the way of field-based research into my classes. I typically hire 3 to 8 students a year to work as part of multidisciplinary teams to actually run the research projects. We have things going on in North Maine Woods. We have this container garden study going on campus right now. And I also do a number of research learning experience type courses. One of them is happening right now, which is a special topics course in biology. It's a research-based course in which I facilitate students co-designing a plant-based experiment in a greenhouse using and based on the principles of Indigenous science and focusing on human-earth relationships. So it's a science co-production emphasis. In the end, it's still doing science. We still follow scientific method, but at the same time, this class is focused on empowering students to work across cultures, to communicate with people from different perspectives, and to learn how to understand challenges and create real world solutions to real world problems. I've also worked with, I have a lot of background in water, particularly in the context of having traveled around the US and Canada as a whitewater boater in years past. I've since built a class built out of a lot of the ideas and inspirations generated from those years called Rivers, Relationships, and Ruins. And the way this works is we have a bunch of students, myself and another registered Maine guide. We meet at the end of the summer and we learn how to plan an expedition and do backcountry camping and take a 4-day trip down the Allagash River, fully self-supported. And through that, we also explore the local history of northern Maine and humans' relationships with the environment, how that has impacted waterways in Maine, and then follow that up with a 1 hour per week discussion session during fall semesters where we develop ideas for how we can reframe and reimagine future relationships with the environment in a changing climate. I'm also going to be starting some new research projects over the coming year, and included in those is looking at and exploring how some of the new nanocellulose-based products that are being developed at UMaine, how those biodegrade under different environmental conditions. We believe that they're going to be highly biodegradable, just like any other paper products. And my sense is that it would be very nice to be able to demonstrate that more comprehensively and also to learn how these products behave under different environmental conditions. Why is that important? It's important because a number of products that are made from things like plants and advertised as being biodegradable don't biodegrade particularly quickly, or they biodegrade in a way that is environmentally problematic. It's also a great opportunity to give to a incoming undergraduate student to cut up pieces of these cool materials, put them in litter bags, bury them in the ground, and stick them underwater in different places and monitor what happens. Dr. Landry and I have also been collecting some descriptive data in different sites around northern Maine aimed at identifying environmental conditions where northern white cedars are more rapidly declining. Northern white cedar decline is a phenomenon that's been much more frequently observed in the past decade, and there's a lot of hypotheses as to why that's happening, but not a whole lot of conclusive evidence for that, for what is causing that or how to deal with it. These pictures, this collage of pictures shown at the right here, I just want to give us some brief overview of these. The one at the top is a bunch of students in a previous installation of my special topics class. They're using the Lycor 6800 photosynthesis analyzer to probe how cedar trees respond to warming conditions and learning how they can use technology in their future lives and careers. That's another part of the experiment at the bottom left, along with one of our Indigenous knowledge sharers, John Dennis from the Micmac Band of Aroostook Band of Micmacs, who is helping us co-administer this experiment with cedar trees. On the right, This is a picture from the Micmac fish farms down in Caribou, where I take my limnology students every other year on a field trip, so they learn about environmental change and its impacts on water quality and building food sovereignty. Also, I'd like to give a shout out to our various community and corporate partners who have been supporters of our work, either financially or um, through various other engagements, such as training students, providing access to land, and providing instruction. So thanks to those folks at Main Tree Foundation, Friends of Cross Lake, Maine Science Fair, Wabanaki Youth and Science, Upper St. John River Organization, Irving Woodlands, Landvest, Maine Youth for Climate Justice, and Maine Environmental Education Association. I'd also like to acknowledge the many undergraduate students and recent graduates who have contributed to making these different research and teaching projects possible. And John, Angeli, and Julie, who I was able to recently reconnect with. John and his new partner just got married down in Vermont. So if I sound a little tired, it's probably because of the 9-hour drive I took to and from over this past weekend. And other folks who are still helping me up here, Georgia, Nick, Kennedy Ashby, who's now moved out to Montana, Ori and Keegan, Rualdo, Morgan, who's been a wonderful student, who is now a student down at UMaine, and Avery, who is applying to graduate school and will, I hope, be able to join us in the fall as a graduate student. Taylor, who supported a lot of this work when she was an undergraduate, and she's now elected to stay with us at UMFK doing academic admin. Sam Bulio, who is our lab manager, and I have perhaps overly at times taxed her with demands for helping support field work and creating messes in the lab. So thank you very much. And thank you also for our major financial sponsors, Bringing Theory to Practice, who catalyzed a lot of the initial work with Indigenous knowledge. Center for Advanced Forestry Systems, NSF score, which have funded the new Maine Forest and Maine Smart initiatives, and along with the Maine Economic Improvement Fund. So with that, I'm going to thank you all for your attendance and really open it up to you for questions and also feedback on how some of the things I'm doing can potentially support the Climate Change Institute in their mission for the future. And perhaps I'll show this beautiful picture of the setting sun, which was taken along one of the bridges here in Fort Kent, where the sun lines up perfectly with this bridge over the Fish River long about autumnal equinox. So thank you very much.
Thank you, Ned. Open up to questions.
By the way, if you're feeling at all sheepish, you're welcome to use the little hand raise in the Zoom bar, or you can just speak up.
I'll start with a quick question. The biochar, is that something that is a byproduct of other activities, or is that something that's commercially developed as a single product?
Great question. So it's some of both, actually. Generally, biochar is available as a byproduct of incomplete combustion. Now, biochar can be synthesized and is synthesized and sold commercially. It's typically synthesized from wood residues. And we're actually working with three different types of biochar. One of those is commercially available through a company called Wakefield. They take those forest residues, make biochar, and then sell that as a soil amendment. I'm also getting biochar from a cogeneration facility out in Greenville, Maine. And their biochar is really a mix of ash and charcoal that's left over from combustion process in a steam plant. And then the third type, which is often called a char, but is, in my opinion, a bit different, is actually a chemical oxidation product left over from chemical synthesis of wood-based biodiesel, which comes from the Forest Bioproducts Research Institute down at UMaine.
Thank you. Sounds like a great use. Any
Yeah,
questions out there? If not, I have another question. As we know, two of the big dangers for forests are pests and climate change. And forest fires are not something that Maine is necessarily thought about in this context, but we know that they're very serious. They're increasing because of increased winds, increased evaporation, lack of precipitation. Uh, well, I guess it was a couple of years ago when Nova Scotia had a large number of forest fires. Makes one wonder, what is there different about Nova Scotia from Maine, and or what are the lessons learned from the Nova Scotia fires that we can use in Maine?
great question. And I don't want to overstep my boundary here. I'm going to start with saying what's different. Serendipity, luck. We got lucky, they didn't. One of the concerns I have, and again, I am not an expert in fire management, one of the concerns I do have is that we've been really pushing for cultivation of spruces. There's a variety of reasons for doing that. Spruces are good for making dimensional lumber. They're also incredibly, incredibly flammable. Anybody who has burned their Christmas tree at the end of the winter knows what I'm talking about. And so I do have some concern that that could potentially make fires more difficult to manage, especially if we end up in a very prolonged dry period. There's also a recent history of dry periods. Southwestern Maine, the area around Rangeley, has been in and out of drought for the past few years. And although the past two summers in the North Woods have been relatively wet, I can remember 2020, 2021, a number of cases where I walked outside and I'm like, wow, I love being outside. It feels just like a Colorado summer. It's 95 degrees out in Fahrenheit, and there's this broiling hot, dry wind blowing across my face, but boy, I don't want to see a spark. So I don't know if I fully answered your question there, but I do think, yes, that fires are a concern, and I think we really need to be very thoughtful about how we manage our forests for that moving into the future. Yes, Katie.
Let's see. Just get online so folks can see me. It's a question kind of related to that. It sounds like the biochar application is like produced elsewhere and then applied to northern forests after you do this testing to see and these experiments to see what the effects on soil and the watershed are. Is there any discussion in that community about applying cultural fire or prescribed fire to northern forests of Maine? So, like in other words, making the charcoal kind of in situ for the same benefits?
That is a great question, Katie, and I actually don't know the answer. I think it would be a good topic to start conversation on. I do know that there has been occasionally controlled burning done, but I think that prescribed burning's mostly been done in a more contemporary forest management paradigm. I think one of the other challenges is this region has historically not been fire dominated. If we move further south, you see a history of Indigenous management with fire. And I'm also going to use some examples looking west of us, west of the Great Lakes, so northern Wisconsin, northern Minnesota, where I used to live and work. And out there, prescribed burning was done a lot and kept the prairies open. But the prairies ended where they did in north central Minnesota and in northern Wisconsin because things were just cooler and wetter and didn't burn well. So without overstepping my bound, I would make a reasonable speculation that fire wasn't a common occurrence up here. But if anybody knows differently, feel free to chime in.
Katie, who used to be with us for many years and now is out in California in, unfortunately, I guess, fire country. Can you add anything? I mean, to your own, in response to your own question?
Yeah, I'm cautious of overstepping bounds too. We don't know a lot about the fire history for northern Maine. And I don't know if it's just like low population or lack of sites. I still co-lead the Northeast Fire and Fire History Working Group. So we're a little under-resourced and kind of slow-moving compared to other research groups to do our work. But we're interested in building this community and some momentum to add to that story and see where historical fire might have been or what fire return intervals might have been for that area.
Thank you, Katie. We hope
Sure.
things went well where you are. I know you're up in the hills.
Yeah, thanks, Paul. Good to see everyone.
Dan, looks like you have your hand up.
Yeah. Yeah, thanks for the presentation. I was just wondering, are you familiar with a company called Ensign Biofuels? They've now done a deal with Castle Rock Green Energy, and they produce a renewable fuel oil from wood. They essentially like superheat wood by passing it through a heated fluidized bed of sand and drive off all the volatiles. And I think they're producing a form of biochar as well. And I was just wondering if you were familiar with their process.
Great question. So I'm not familiar with that particular business, but I have read a couple of articles in engineering journals about that process. I don't really have a whole lot more I can add to it other than that type of a thermolysis process is something that's being done, and I suspect they're probably not the only business going down that pathway.
No, I think they're proposing to build a 20 million gallon facility in a site of an old mill in central Maine.
I might add one more quick detail in response to that your question, Daniel, is that my experience working with the quote biochar from the Forest Bioproducts Research Institute, even though it's called biochar, it's chemically a very different material. We see that in the physical texture. We see that in the infrared spectra that we've collected on it. And it has very different behavior in the soil. It acts a lot more like peat moss. It starts out very acidic. That problem can be solved by buffering it, but we do see much higher soil respiration rates when we buffer it and then add it to soil. And also, Katie, just to briefly follow up with your comment, I would love to chat further about potential opportunities for exploring fire history in Maine. And I don't know if anybody else had, I think we've got a few more minutes, although I'm not in a strict hurry of any sort.
I don't see any other questions out there, so thank you very much. I should mention that Dan Dixon is the Director of Sustainability for our university. And Katie, obviously, she told you what she does and is now in California, but you might want to also get a hold of Sean Burkle, who's the Maine State climatologist attached to our institute, does a great deal with climate predictions, understanding modern climate, and I'm sure there are many other people out there that look forward to talking to you in the future. We have I think it's in late April this year, we have what's called the Born Symposium, where people come and give an AGU-like, which means 10-minute presentation. We'd invite you, students, to come down for that if you would like to, and look forward to the future and collaboration.
Thank you very much, and I'll definitely keep that opportunity in mind. And likely we'll follow through if it doesn't overlap with we have a special event, I think it's the 28th or 30th of April, for students to present their research up here. And one of those things about teaching at a PUI campus, I always prioritize student presentations above everything else.
Ideally, we do too. So thank you very much. Great to hear from you, Ned. Very exciting work, and thank you to all who attended.
Thank you as well.